Okay, welcome to the Winstop meetings. Today, Saidu, if you like, you can turn on your camera if you want. Today, we are having Saidu as a speaker. He's going to present us the quantum internet, a brief survey about this recent hot topic on quantum communications. Okay, Saidu, the floor is yours. You can share your screen and start. Okay. We don't see the screen, Saidu. No?
Can you see it now?
Yeah. It's there, right? I'll see. Thanks.
Good afternoon, everyone. My name is Saidu Sokoto, and today I'll be talking about the quantum internet, its applications, current breakthroughs, and the challenges that need to be overcome. So the flow of my presentation today is going to be as follows. I'll start with some background information, then move over to some specific applications and use cases. After that, I'll talk a little bit about some breakthroughs that the quantum networking realm has seen. And then finally, I'll talk about the challenges. Moving on to some background information. When the quantum internet is mentioned, there are certain terms normal networking people or computer science students are not familiar with. These terms include qubit, the entanglement, superposition, no cloning theorem, and a host of other terms. But I'll define around 5 terms in this slide. We have the qubit, which is the fundamental unit of information in quantum communication. It can either take the value of a 0 or a 1, which is represented by the basis state. However, it differs from the classical bit in the sense that it can also be in a superposition. It can be in a combination, linear combination of both a 0 and a 1. This is before measurement, though. When the qubit is measured, it collapses into either a 0 or a 1. This is a very important characteristic of the qubit, which will be used in quantum networking. We also have entanglement. This is a situation where two particles share a state whereby any operation that affects one particle or any operation that occurs on one particle affects the other particle and vice versa. We also have the no cloning theorem. This theorem basically states that creating an identical copy of an arbitrarily and unknown quantum state is impossible. Copying is impossible, basically. Finally, we have teleportation. Teleportation is used for transferring quantum information from one node or from one entity to another. It should be noted that in teleportation, the actual qubits are not transported or transferred. It's only their states are transferred. These terms there are a lot of other terms. We will see them during the presentation. I just felt like these terms are the absolute necessary. Familiarity with these terms are absolutely necessary in order to understand some of the things I'll be discussing during the presentation. So before moving on to the actual applications, I would like to give a brief difference between the classical internet or the classical networks and the quantum networks. As computer science students, whenever quantum is mentioned, I'm not sure about others, but I used to have this jitter in me. I thought it was specific to the realm of physics or mathematics, but as we'll come to see, there's some inherent differences, obviously, but then there are also contributions we'll be able to make. So qubits pose a limitation. The structure of the qubits make it impossible to copy. It makes it impossible for error detections and corrections that we're familiar with. Why are these things impossible? Well, in the classical networks, we're able to resend the packet if it fails or something like that. This is not possible in quantum networks. We're trying to minimize error correction as much as possible. And Another property of quantum states is that they're usually affected by the environment they are in. So quantum's decay, there are a lot of other things that affect quantum bits. We also have the impact of photon loss. If a photon is lost, we assume at the end of the day that the whole qubit is lost. Quantum operations are also highly probabilistic in nature. We have entanglement, which is also such as things like entanglement. This is also a probabilistic thing. So the aim in quantum networking is to increase the probability of a desired state as much as possible, while decreasing the probability of an undesired state. The concept of throughput is also different in quantum networking. While in the classical sense, at least theoretically, the throughput of a hub-by-hub network can be maximized. In the quantum sense, as the number of hops or as the number of entities increase, the fidelity of the quantum state decreases, and also a host of other issues arise. I just recently mentioned the concept of fidelity in quantum networks. Applications have fidelity requirements that have to be met. These are all things we don't see in the classical sense. And these are things that make the quantum network different from the classical networks. While in the classical networks, we transfer bits, packets are forwarded from one node to another or from one host to another. In the quantum networks, services or entanglement is shared. And these makes it a lot different than what we're normally used to seeing in the classical networks. After this basic background information, I'm going to move to the applications. There are different ways of classifying applications. C1 and others in a recent memo they submitted to the Quantum Internet Research Group provide this classification. They classify it based on the application domain into three. We have the quantum cryptography, which focuses on cryptographic tasks. And then they also have the quantum sensors, which is basically having distributed quantum sensors making use of the quantum internet to exchange entanglement. And then finally, we have the quantum computing. The quantum computing is making use of the quantum internet at the same time to achieve some computational tasks. We're going to see in the upcoming slides examples of each of these applications to clarify and to give actual examples of what they do. So under the quantum cryptography, we have two examples here to show what quantum cryptography means. We have the secure communication setup. I believe this is one of the most famous examples of or the most well-known example of the use of the quantum network. We have, for example, we have the quantum key distribution, right? In the picture here, we have two nodes, for example, a bank 1 and a bank 2. Let's say they want to exchange some confidential information. Well, they can use a quantum internet to exchange quantum keys or secure keys. The banker at the left side or an end node might initiate this key distribution. After the keys are distributed, classical internet can be used for subsequent communications. This is an example that shows that the quantum internet and the classical internet can work side by side. As a second example, we have the fast Byzantine negotiation. This is the use of quantum mechanisms. This is the use of quantum mechanisms to achieve agreement in quantum in Byzantine negotiation. Um, Using quantum repeaters or using quantum networks will result in faster communication times. So it will reduce the round trip time, resulting in faster agreements when compared to the classical Byzantine negotiation. And this will hopefully result in improvements in consensus protocols such as the practical Byzantine fault tolerance. Moving into a second application domain, we have the quantum sensor networks. Uh, well, exactly as quantum sensor networks, similar to the sensor networks you're familiar with, but in this sense, they're distributed in nature and they make use of quantum internet, which makes use of quantum repeaters and long distance entanglement distribution to achieve some tasks that are not normally achievable in the quantum network. Some of these tasks include the network clock synchronization. As we're all aware, we have atomic clocks, which are very precise. However, if we're able to leverage on the quantum internet and connect them with each other, the precision may be increased to a whole new level. We have high sensitivity sensing. We have the molecular tracking, environmental and health monitoring, timing, which is similar to the network clock synchronization, position and navigation. In a recent paper I was reading, they even talked about the concept of no GPS tracking. These are a whole lot of applications, and hopefully we will see some innovative things coming out of the quantum internet in the near future. We also have the quantum computing. As an example of quantum computing applications, you can have distributed quantum computing. This is a situation where we have remote nodes or remote low power nodes which have low qubits, for example, or a small amount of qubits distributed and communicating with each other, of course, in coordination, communicating with each other using the quantum internet in order to simulate a virtual large-scale quantum computer. In addition to this, we also have the secure quantum computing with privacy preservation. This is I was impressed by this. For example, if we have a terminal node, it can make use of the resources of a remote quantum computer using the quantum internet. Well, the caveat here is the privacy preservation. The terminal node is able to use these resources without revealing either the input or the output or the algorithm that the quantum computer, that it wants the quantum computer to use. So complete preservation of security is achieved here. You can ask, of course, even now we can use cloud computing to relegate some tasks, but is this privacy achieved? Maybe not. The quantum internet, this privacy is going to be achieved. Well, we have talked about classifications based on the application domain. We can also classify applications based on the data plane or the control plane, as we usually know in the classical sense. In the classical sense, we know that the control plane is responsible for determining how a packet is forwarded, while the data plane does the actual forwarding. We can decide to thread the same path in quantum computing. So in this case, how will the applications be divided? We all know that in the classical internet, we have the control plane, which has examples such as the internet control message protocol or the domain name server. In the data plane, we have video conferencing, for example. So if we're talking about purely quantum internet that's not connected to the internet we currently use, we can have a quantum ping, which might be used to test whether two or more nodes are two nodes are connected to each other. This is a task, of course, in the control plane. We can also have signal for controlling entanglement distribution. In the data plane, I should have mentioned this earlier, but in the quantum internet, of course, our qubit or our quantum state is the actual data. So we can have the quantum key distribution. We can have entanglement distribution all as data plane services. However, in the hybrid internet, whereby the classical internet and the quantum internet are living in harmony, hopefully side by side, we can have the quantum key distribution based secure communication setup. We have already seen this example earlier as a control plane, and we can also have the video conferencing using quantum key distribution based secure communication using the data plane. Of course, in the future, these might be different. We can have one control plane for the quantum internet and a single control plane for the classical internet, while they share the same data plane, or the other way around. We can have one data plane for both the quantum internet and the classical internet, and a single control plane for both, which makes more sense. These are all ideas, and hopefully we will see real applications. So what are some breakthroughs that have been achieved so far in the research related to quantum computers? Well, while I wouldn't say I'm proficient in physical layer achievements, all the work we intend to do or that is yet to be done in the networking domain has to rely on achievements made in the physical layer. So a large chunk of hardware problems have already been solved, and the necessary physical means of achieving quantum network already exist. We have quantum memories, we have different labs in the world focusing on different areas. We have some labs focusing on atomic ensembles. We have some labs focusing on single atoms. And recently in a webinar organized by the Quantum Internet Research Group, a presentation presented by Mahdi Namazi, he gave room temperature solutions. Even though I didn't understand a lot of the things he was saying, I got some motivation to look more into quantum networks, at least by the room temperature solutions. We have entangled photon pair sources, we have quantum gates, we have single photon detectors. These have all been achieved so far. But as we will come to see in the upcoming slides, there's still room for improvement. This is a rapidly developing field, and every day new advances are being made. And something more related to us, what has been achieved in the networking domain. So we have different proposals. We have the layered architecture model here, similar to the OSI model we're used to seeing in normal networking domain. For example, here in a protocol stack architecture proposed by Van Meter and Touch, they propose this form of architecture where we have 5 layers. We have the application layer, error management, we have the remote state composition, and link level entanglement, physical layer. The only layer here that deals with the qubits in the actual sense is the physical layer. This is an example of a 5-node for hop connection. To emphasize their points, they even gave some protocol examples. For example, on the right side, you can see some purification control protocols, entanglement, swapping control protocols, and others. A lot of details can be found in their paper, which they termed quantum repeater protocols for quantum repeater networks. At the end of the presentation, you'll be able to see a link to their paper, which was published around 8 years ago in 2013. So these architectures have limitations, of course. The internet, the quantum internet is yet to be achieved, and there's a lot to be seen. But the protocols they propose at least serve as a building block for new ideas to be developed. Moving on to other things like multiplexing, which is basically how resources or channels are shared between competing entities, and how quantum memories, of course, if we're talking about the quantum internet, uh, how quantum memories are managed, all these things. Different multiplexing schemes have been tested already, at least using simulations, and statistical multiplexing has been checked. Time division multiplexing has been checked, and there is still room for improvement, of course, but at least, like I mentioned earlier, there is some work that we can build on. Routing, how will routing be achieved in the quantum internet? Can we make use of Dijkstra's algorithm? Well, to some extent, if you have a middle level network, not an extremely complex network, Dijkstra's algorithm seems to be a feasible solution. But once the networks become bigger, we have an internet of what's going to happen. Once we have different organizations having their own internal rules, what's going to happen? Rodney Van Meter has proposed the CODA. Is this an option? Well, it relies on the quantum repeater network architecture. Some of us may be familiar with repeater networks and the classical networks, or whereby internal networks of organizations are usually abstracted and made to look like simple relay, so as to simplify addressing and other issues. This is the path he seems to be threading for his research and suggestions, but whether or not this will be accepted in the future is still open to debate. And of course, a host of other solutions might be presented. So we have seen current breakthroughs. Of course, those breakthroughs are also challenges, and there room for improvement. All the solutions proposed are not written on stone, and there might be some improvements made to them. But what are some challenges that we still have to overcome? Well, we have the transmission management. How are we going to, we already have everything in place in terms of the physical solutions needed, but we do not have a robust protocols in place to manage the transmission of quantum states. Quantum key distribution, so far it seems like the most profitable, most feasible applications of the quantum internet. There's still room for research. Standardization is hasn't still been achieved, and a host of other issues. Management in the quantum internet, we might have how will we deal with congestion in the quantum internet? The protocols being proposed, how are we going to verify them? Do they work as claimed? Interconnecting different schemes is also an issue. Each organization is going to run its own internal, for example, routing algorithm or whatever. How are we going to interconnect all these things together when we finally have the quantum internet? These are all things that are open, and different people's input will contribute to the success that is yet to come. So we still don't have quantum repeaters per se, but this is also an open research area. The building of quantum repeaters, strides have been made and are being made. It's still open to improvement. Security is still a very big challenge. All the assumptions made about the quantum internet is based on the claim that all the nodes are working as expected. But in the real world, we all know that there will be malicious entities. How are we going to deal with that in the quantum internet? So with that, I have come to the end of my presentation. we have seen different use cases of the quantum internet. Despite that, we still need a network architecture that is going to be able to deal with complex topologies, the needs of different organizations, deal with link failures, and a host of other problems. Despite the terms being fanciful, such as entanglement, teleportation, I believe these are things that will play a vital role in the evolution of the internet, of the quantum internet, and a host of new services that we're yet to see. Thank you very much for listening. And if you have any questions, I'll be glad to answer at least the physical, non-physical questions.
Saidu, thank you very much. Are there any questions, Saidu? I don't see any questions on YouTube platform. Any questions from the online participants? So when it comes to the quantum entanglement, what is the most important, significant challenge that we have to solve the first side?
I believe right now, Professor, it's the building of the quantum repeaters.
Quantum repeaters.
There's routers we have in the classical applications. The applications you'll find in a standalone quantum computer. A standalone quantum computer, you can have a random key generation. No? We're trying to achieve distributed computing now, but you need to forward the quantum states. Different proposals have been made using the store and swap. They have this term in the quantum mechanics whereby they use swapping where you sacrifice a Bell state. Whatever the case, I think the quantum repeaters are the current bottleneck.
Are there any demonstrations up until now?
What, sir?
Are there any demonstrations right now where they can do more than one home?
Yes. Recently, about 3 days ago, there was a publication on the 16th whereby 3 nodes were connected, and it is claimed to be the first quantum internet, because two nodes are not considered an internet. So 3 nodes were able to communicate with each other in TU delta, I believe.
TU delta, okay.
Yes.
Okay, Saidu, thank you very much. Are there any other questions from the audience? I believe not. Let me stop the stream.